Yes, I just do it because I want to solve this in a landscape. The previous one is horizontal one. So let's move on. We have a data. We have initial mass, that is 25 gram. P1 is 300, current is 0.2, voltage is 120, and heat loss, that is Q, is 120. So we write this on here. 25 gram, P1 is 300 kilopascal, and we have voltage source of 120 volt. Current can be written like this, 0.2 ampere, and anything which is left to 120, and like Q is 3.7 kilojoules. The heat loss is 3.7 kilojoules. So this is data, and now we are going to solve the numerical. First of all, we have applied the same equation of energy balance for the closed system, that is delta E of the system is Q minus W, and delta E is sum of KE plus PE. So kinetic energy plus potential energy plus delta U internal energy is equal to Q minus W. Here we've cut out this 0. There's no kinetic energy because the thing is not creating any motion outside the boundary or surrounding, so it is 0. But in the whole system, internal energy is increasing with increasing the temperature provided by the heater. So basically, heater is providing heat in the steam, which makes his steam into superheated steam. First of all, we have to decide that the initial state, whatever they have given us, they are state of saturated steam at that 300 kilopascal, and when it is heated up to some extent by providing this energy, electrical energy, it is going into the superheated form. So first of all, we will see the graph of A4 or A5 of saturated steam, and then we move forward towards superheated steam. So by opening this, we can write this like U2 minus U1, delta U is equal to U2 minus U1 is equal to Q. So it is heat loss from the system or gain from the system, we have to see, and then we have to mark the sign accordingly. So in this, at the same time, heat loss of 3.7 kilojoules occurs. So it is heat is losing from the system is 3.7. So we have to write this with the negative sign, minus 3.7 kilojoules. Remember that we are putting here with the kilojoules. So the remaining unknown we will get after this, it is also in the form of kilojoules. And we have two kind of work over here. First work is W electrical, and the electrical energy, that is also a form of work. In thermodynamics, we study the electrical energy in the form of work because it is producing capability of steam to do pressure volume work. So it is also form of energy. And what is the formula for the electrical energy? W electrical. What is the formula of electrical energy? Is voltage times current times multiply by time. Voltage times current multiply by time. So it is electrical energy unit. You also get the unit in the electrical bills like kilowatt hour. So basically it is a unit of energy. So they also told us the time duration. We didn't 5 minutes, so we also mentioned time in the data, that is 5-minute time, and we need to convert this 5 minute to second, that is 5 multiplied 60. So here I just want to write with, we don't get much space over here, so I can write this again, the proper form u2 minus u1. This goes to here, that is q is negative 3.7 because heat is losing from the system. But we have two kind of work, W electrical and W electrical heat. W electrical work is added to the system. So W work is work act oppositely with the sign of Q. So any work added to the system can be write with the negative sign, W electrical and P delta V. It will the work done by the system in the pressure volume work can be in the form work done by the system. So if work done by the system, we write with the positive, and we write with this PV or WM, electrical and mechanical. Two work, we have two work in the system diagram. This is electrical work, and with the piston going up, that is a mechanical work. And in the lecture number 5 and 6 I also show the diagram of conversion of how the electrical conversion, how the mechanical work is conversion into the electrical work. I have shown in the diagram also in previous diagram. I will show in later after this. Like this in picture, I have shown this picture in previous lectures, that this is basically work. The mass is moving this paddle, and this paddle is moving the shaft of a generator, and the shaft is producing electrical energy. It is converting heat in the system. So basically we can write this electrical energy in terms of mechanical, in terms of work in thermodynamics. This picture best explain why we are using this electrical energy in the form of work. So negative, the formula's negative sign is over here, so when we multiply minus minus, it becomes positive. So u2 minus u1 is equal to minus 3.7 plus W electrical minus W mechanical. Now it is in the electrical minus sign, we shift this mechanical over here. So u2 minus u1, it is in the minus form, we can write this W mechanical, and we also open the mechanical work, that is P delta V, V2 minus V1 is equal to minus 3.7, and we can also open this electrical work with V I multiplied by T. So it's a electrical work. I also show this over here, and this mechanical work is basically P del V. In previous lectures, and especially polytropic process, we studied that system with the equation of work is equal to integral P dV. So it is an accurate form, but here we don't get the equation of process and the value of N. So we can take the basic equation of work, that is P delta V, and now we are arranging this equation in the next form. We can write u2 with PV2 and write u1 with PV1. U2 plus P V2, we multiply P with V2 and we take minus as a common. In the U1 we have negative sign, so we make it minus common, so we also get PV1. Now you can that this is multiplied by P multiplied by V2 is plus PV2, so we arrange this with this and we take minus as a common and write U1 plus PV1, and this minus also taken common from the bracket, so it is minus 3.7 and 120 voltage, current is 0.2, time is 5 multiplied by 60, due to the second, it is time, we make it in the second. So now this is U2 plus PV2 plus U1 plus PV1 is basically what? Enthalpy. We already studied that property in our previous lecture here. So enthalpy is basically internal energy plus pressure volume work. It is a sum of or combination of internal energy plus pressure volume work. So we can write this with the capital H2 minus H1, and we can write this minus 3.7 plus if we multiply by this whole, we get the answer. So by multiplying this whole, we get answer 7200. This is equal to 7200, but we take this Q loss in the kilojoules, so we also need to divide this by 1000, so then it becomes 7.2. And when 7.2 minus 3.7, it gives answer of 3.5. So we get the answer 3.5 kilojoules. Now we can write this with the specific enthalpy, because in the steam table we have a specific enthalpy H2 minus H1, and we know the initial pressure 300 kilopascal, so we also can get the value of H. First we H, so we know the value of initial pressure, that is 300 kilopascal. So from the graph from the table saturated water steam table A5, we can get the value of H1 initial. We are given with the initial pressure, so we are looking of A5. If they given us a temperature, we will find out the in the A4 graph, A4 thermodynamic table. So along the 300 parameter, we get the initial enthalpy, that is Hg. We have to see Hg, and this is Hg, so HF Hg. We have to highlight this value up till this point. So if we minimize this value, this is Hg. You can see we have to check value of Hg, that is 2724.9 across the pressure and Hg. Why we didn't take HF or HFG? Because they told us that it is in the initial state, it is in the form of saturated vapor, so it is in the Hg phase. So we taken this value is 2724.9. we can write this over here, 2724.9 at the rate 300 kilopascal H1. In the paper you can write in the middle of solution like this from, and also give the reference from A5 table. And now this mass on the other side, it is multiplied over here, goes with the division. and they given us with the value of gram, so we should also convert 25 gram into kilogram. So now it has become 0.25, 0.025. So 0.025 goes over there, and in this way H2 minus 2724.9 and 3.5 divided by 25 divided by 1000 because it is in the gram. So on the other hand, this it is in the minus, on the other end it goes with the positive. So H2 becomes 2724.9 plus this 3.5 divided by 0.025. So it is 140. 3.5 becomes 140, so we can get the value of 2724.9. So we get the value of 2864.9 kilojoules per kg. Now we get the enthalpy at phase 2. When we given heat, when we give heat, when we heat the system with the electrical resistance with the voltage of 120.2 current in with 5 minutes, when we providing heat up to the 5 minutes with 120 volt and 0.2 current, the system goes or increase the enthalpy up to 2864.9 from 2724. So this is the H1 is, this is H1 basically. So in this, just in the 5 minutes, the system increase or elevated the enthalpy. Correspondingly, we know that the steam table, it is also in the form of temperature. So from this enthalpy, we get the final enthalpy of the system. So when we in initial state, we get enthalpy from the initial pressure, that is 300 kilopascal, and get the value of final enthalpy in the correspondingly the same way. From this enthalpy, we can also calculate the temperature. We can also calculate the temperature from this enthalpy. You know how? From the same steam graph. Now, but in the different steam table. Now it is the when we heat this saturated steam further, it will not stay in up to saturated state. It will become superheated state. So from this even diagram, PV diagram, you can see that this is wet dome and this is saturated. It goes into the superheated region. So we need to see the graph of superheated state, and for the graph we have to find out. This is graph of saturated water. This is also saturated water. Now this is superheated water. It is the graph of superheated, and now the pressure becomes constant. So we again see the values in 300 kilopascal, and if we the conversion of kilopascal into megapascal is simple. Divide 300 kilopascal with 1000, so it becomes 0.3 megapascal. So 300 kilopascal is basically 0.3 megapascal. So we goes into the graph of 0.3 megapascal because the pressure is constant from one state to two. So even in the final state, the pressure is 0.3 or 300 kilopascal. So along this we have to see enthalpy, the 1 2 3 third property, third property. So when we coincide this enthalpy, we can get the temperature across it. So now we have to see what we get the answer in the, that is 2864.9. So any value that is close to 2864, we correspond this with the temperature and we get the final answer. So we get 2864. So it is 2807. Is this third property? We have to see. So it is very close. Yes, 2865. We get the answer 2864, but the values in the table is 2865. So it is almost we get the value that is 250. It is very heavy pan, so the first one is saturated pressure, and saturated pressure written over here, this is saturated pressure, and after that we increasing the temperature with the increases of enthalpy. As we increasing the temperature, the enthalpy will increase. So the final enthalpy is 2864, that is close to 2865, and across this temperature it is 200 degree centigrade. Yet the unit is degree. So now we have done this numerical at now we can write at H2 and 0.3 megapascal from table. We give reference from table. It is table A6. Table A6. T2 is 200 degree centigrade. So this is in this way we have calculated that we solve the answer. In the later we will solve further numerical, inshallah. Till then, Khuda Hafiz. Assalamu alaikum. Bismillahirrahmanirrahim. So now today we will cover lecture number 10th of fifth week. In the last lecture of 9 we have covered some example of steam cycle, like only one process, like for the heating process from saturated steam to superheated state. It is TV diagram. In that numerical we have PV diagram, so pressure is constant. But now if I draw the similar thing like this, it will goes like this, not like this. Okay, now move on. The why it is making problem. Like, so we have read out some new terminologies like vapor pressure, dryness fraction, and quality of steam, and that critical point we already studied in lecture number 8. So let's move on. Enthalpy, etc. Latent heat and sensible heat, and the two form of latent heat of one is the latent heat of vaporization, and one is the latent heat of fusion. And this is numerical we have done in the last lecture, example number 4.5 from the Sengel. Now from this example you get an idea that how the steam is utilized in power generation cycle. It is not only utilized in the power generation cycle, but it also used in many industries for the process. Like we have 60 ton of boiler, 60 ton per hour of steam generation in General Tire, and it is not used for the power, it is used for heating or curing the tire. So it can also be used in many industry for heating purpose, in heating purpose, or in any heating purpose in their processes, like in chemical plants, refineries, all wherever you go you find a big boilers working behind every process for heating process especially. This process is also available in our mechanical engineering lab. We have an electrical boiler which heat water from the steam and then steam into the not only it is used till the saturated state, but here in this example we heat saturated steam to superheated state. This is the solution we have done in the last lecture. Now in the last lecture I've told that I will show some of animation of their application. In our course content we have heat cycles, thermodynamical cycle, and thermodynamical cycle we have majorly two cycles: Carnot cycle, and its another form reverse Carnot cycle, and Rankine cycle. So Rankine cycle is very lengthy, so I just cover the basic introduction of here. Now how it is utilized in the power generation sector. Not we are not doing its numerical because its numerical is very lengthy. So the course content only shows cycles. So I just cover Rankine cycle in your course content, Carnot cycle in your course content, and Rankine cycle just we have done one numerical, not a complete numerical, just one part of heating process. If we going to the complete cycle, you will see in the animation that the complete cycle have different processes behind the complete cycle. So we cover only one process in this example, and just for your information, I just added animation and videos so you can get idea of Rankine cycle.
Today's engineering topic is Rankine cycle. So what are we waiting for? Let's start this right away. Rankine cycle was named after a Scottish polymath and Glasgow University professor, William John Macron Rankin. It is a vapor power cycle. For a little definition, power cycle is a cycle which uses heat to generate work. And since it's a vapor cycle, it uses the vapor phase, or in this case, steam, to rotate the blades of the turbine. It actually utilizes the heat energy contained in coal, oil, or natural gas, and it converts it into mechanical energy and eventually electrical energy, which of course provides electricity in our city and in our homes. One of the best definitions for this cycle is that it closely describes the process of steam turbine systems and is derived from the Carnot cycle, the most efficient thermodynamic cycle, which tells us that power is dependent on the temperature difference between a heat source and cold source. The higher the difference, the more mechanical power can be efficiently extracted out of heat energy. So now, let's talk about the variants or the types of Rankine cycle. We have a reheat Rankine cycle. It is a cycle which we introduce the exhausted steam back into the boiler to reheat it. We also have a regenerative Rankine cycle. We bleed apart the steam into heat exchangers to preheat the feed water before entering the boiler. There is also an organic Rankine cycle. It uses an organic high molecular mass fluid with the boiling point occurring at lower temperature than the water-steam phase change. A supercritical Rankine cycle is also one of the types. Just like reheat and regenerative Rankine cycle, water is the working fluid, but it is separated.
Yes, supercritical Rankine cycle are operated by HUBCO Power Plant. Recently they have installed, like in previous lecture I've told that some of the students get appointed in HUBCO and they are operating this kind of supercritical Rankine cycle, in which the water directly converts into steam. There will be no phase change process because it is operating at very high pressure, like 22 megapascal, like we have discussed in the previous cycles. So let's move on, and we have done only this process from saturated steam to superradiant state. In the previous example 4.5, we have done only this part of the process. For complete cycle, it's a very lengthy numerical, so we are not covering here, and it is not also our course content. So we just move on with the introduction.
At above is critical pressure. So those are the types of Rankine cycle. But here, on this video, we will only discuss the most basic and fundamental of the cycle, the ideal Rankine cycle. We must be aware first that this operates slightly different than the real Rankine cycle. This is a reversible cycle. Common sources of irreversibilities are neglected, such as frictional pressure drops and undesired heat transfer with the surroundings. A constant pressure or isobaric process and constant entropy or isentropic process are used for the equipments involved in the cycle. The working fluid is water, and it will undergo a closed loop and will be reused constantly. So why do we use water as the working fluid? Well, simply because it is not toxic, not reactive, highly abundant, low cost, and good thermodynamic properties. To make a Rankine cycle, we need 4 processes. Process 1 to 2 for the boiler, process 2 to 3 for the turbine.
So in the lecture example 4, 5 and 5 we have covered only this part. It is a sub part of boiler. Boiler is starting from this to this. What is heating from subcooled liquid to superheated steam. So we just cover only this part in example 4.5. So covering all these parts, it's become lengthy. So we just left with the introduction.
Process 3 to 4 for the condenser. And finally, process 4 to 1 for the pump. And that is what we are going to discuss for the next part. Okay, so let's get this started.
So I just revise once again that from process 1 to 2 is for the boiler, where the water is converting from liquid state to superheated state, not only gaseous state but superheated gases like superheated steam. And turbine is converting that pretty much high pressure temperature into mechanical power, and that mechanical power which run electrical generator, and it produce electricity, and the remaining condensed steam. Now this at this point that steam is at very low pressure, it cannot be utilized further, so we have only choice to convert again into the water. So in this from first to 2 we are converting water into steam, and from 3 to 4 we are converting steam mixture of water and steam into complete water. Why? Because there's no such any device which can increase their pressure directly. From the gases we have a device called compressor, and for liquid we have a device called pump. So the power input of the compressor is pretty much high, so we cannot pressurize this fluid through compressor. It is very expensive process, so the efficiency of the thermodynamic cycle becomes lower. So the easy way to increase the efficiency or increase the pressure of the working fluid is done by the pump. And pump easily pressurize the water, because water is incompressible. You know that in the liquid state the water is incompressible, it cannot compress further, so any pressure applied on it will increase the pressure. But whereas the gas can be compressed, so we need to apply lot of power, because when we are applying the power it is compressing, and the pressure rise becomes very expensive. So that why we convert steam, that mixture of steam and water in complete into the water, and it is very easy process. In later video you see that by natural seawater we are converting this steam into water. It's very inexpensive process, and it is abundantly available. Most of the power plant, like I'm give an example of Hubco, it is also situated near the sea of Balochistan, Hub River and sea. It is situated between these 2 points. So by the stream of natural river, it easily and without any expense of energy or importing any fuel, we easily convert this saturated vapor into water form, and then we pressurize it with the pump, and the pump required very little power. Okay, I hope you can get an idea why we are converting this. When we convert this into the steam, then why we are converting again into the water. That is the reason.
For process 1 to 2 boiler, these are the things that we need to remember. Since boiler is a heat exchanger equipment, a heat is added into the boiler through a fuel, which may be coal, oil, or natural gas. Here, water is converted into steam or superheated steam. This is an isobaric process or a constant pressure process. The temperature and entropy for this process increases. And we can solve the heat addition by using the formula heat added equals fluid energy out minus fluid energy in, or enthalpy out minus enthalpy in for the boiler. Note that this equation is formed by using a mass and energy rate balance for a controlled volume at steady state, neglecting pressure drop. So those are the important things that you should remember with understanding the boiler process. Now, steam can be used in the next process, which is the process 2 to 3 turbine. Turbine is a work generator equipment. It contains series of stages or a set of stationary and moving blades to perform its function. By using the steam, work is generated through the expansion of vapor, which may then be converted into electricity through generator.
So this is steam rotates this turbine blades, and by moving of the shaft it is connected with the generator, and then generator is producing high voltage electricity, then can be transferred by the transmission lines to our domestic or commercial areas.
Compared to the previous process, here, since we have an equipment that involves work, isentropic process or constant entropy process is assumed. Yes, it is assumed because in real world, there is no such thing as ideal. On this process, the temperature and pressure decreases. And the formula for the work is fluid energy in minus fluid energy out, or the enthalpy 2 minus enthalpy 3. Note that equation is formed by using a mass and energy rate balance for a controlled volume at steady state, neglecting heat transfer with the surroundings. Steam is now already exhausted, and so we need to take it back again to the boiler, but there is no pump that can pump steam, so we need to convert it first into water through condensation. So this is where our next process comes in. Process 3 to 4 condenser. In order to condense the steam, a heat rejection must occur. Most of the power plants utilize the seawater as a cooling medium to cool down and condense the steam.
So this is what I'm talking about. In Hubco power plant, they are utilizing river water. They are passing river water, and it is not mixing with the steam. It just only transfer heat. Like in the steam, in the mixture of steam, we have a temperature, but the form is steam. So when it's contact with the low temperature water, like river water temperature water is more than is like 23, 25 or maximum 30 degrees centigrade. So when it contact with the steam condense, then steam is change its form from mixture of steam and water into complete water, and that water again utilized in the pump. And
Condenser consists of tubes to accommodate the heat transfer of steam and cooling water, where cooling water is in a separate stream. This is a heat exchange equipment, so we assume that this is an isobaric process or constant pressure process. The entropy decreases, and the quality of the fluid changes until it reaches a saturated liquid state, so from steam to liquid. The equation is heat rejected equals fluid energy in minus fluid energy out, or enthalpy 3 minus enthalpy 4. Note again that this equation is formed by using a mass and energy rate balance for a controlled volume at steady state, neglecting pressure drop. process is process 4-to-1 pump. Pump's main purpose is to convey and introduce back the condensed steam to the boiler. Here, work is needed. That means work is negative. Some plants name this pump as boiler feed pump, and it can be either steam-driven or electric motor-driven. Again, since this is a work-involved equipment, we assume that this is an isentropic process or constant entropy process. The temperature slightly increases, and the fluid is in a subcold region in the TS diagram. The formula for the pump is work equals fluid energy out minus fluid energy in, or enthalpy 1 minus enthalpy 4. Fluid energy out or enthalpy out is greater than the enthalpy in, as the pump have imparted energy to the fluid. Note again that equation is formed by using a mass and energy rate balance for control volume and steady state, neglecting heat transfer with the surroundings. And one more important thing, please remember that the pump has the highest pressure in the whole cycle. Okay, so let's have a recap. Starting from the boiler, we convert the liquid water into steam. Introduce it into the turbine to generate work, and then we condense it into the condenser and pump the liquid water back to the boiler through a high-pressure pump. So that's it. Engineering is a fun thing, and it always has been. See you again for our other easy and fun engineering topics. Easy engineering topics made easy and fun for you.
So you get idea of how the steam power plant works, and we just solved heating saturated steam to superheated steam. So all that process comes thus if we sum all the process, it can be for the power generation sector. And not only this, this saturated steam also used for process as discussed before. So now we will move forward another topic.